Hello all, I am Dr. Rizvi, and in this lecture we will discuss torsion of shaft, the assumptions made while deriving torsion equation, and we'll also discuss the derivation of torsion equation. So let us start with the torsion of shaft. If we have to transmit energy by rotating a shaft, we need to apply turning force. There may be cases when a tangential force is applied in the plane of a transverse cross section. Then the torque or the twisting moment in that shaft can be calculated by multiplying the force that is applied on the shaft tangentially with the radius of the shaft. In another case, if the shaft is subjected to two opposite turning moment or twisting moment, then it is the condition of pure torsion. And in this case, it will exhibit the tendency of shearing off. That means tearing off of the every cross section that is perpendicular to the longitudinal axis. So this is torsion of shaft. Now we come on to the assumptions that are made while deriving torsion equation. Assumptions. The first assumption is the material of the shaft must be homogeneous. That is, it should remain same throughout its length. The second assumption is that on the application of twisting moment, the circular section must remain circular even after the loading. This is the second assumption. The third assumption is a plane section of shaft normal to its axis before loading should remain plane even after the torque is applied. The fourth assumption is that the twist along the length of the shaft should be uniform. That is, when the shaft is being twisted, the twist must be uniform throughout its length. The fifth assumption is that the distance between any two normal cross section remains same even after application of such as if we apply if we cut these two sections, so the distance between two sections must remain same after application of torque. No lateral displacement is observed. The next and last assumption is that the maximum shear stress that is induced in the shaft due to the torque must not exceed the elastic limit. That means the stress should be directly proportional to strain and it should be within the elastic limit. So these are the five assumptions that are made while deriving the torsion equation. Now let us start with the derivation of torsion equation. Initially, we know that this is a shaft that is fixed at one end and the other end is free, and we have applied a torque T or twisting torque T. This is the maximum twisting torque that is applied. Let the diameter of the shaft be capital D. I suffix P be the polar moment of inertia. Polar moment of inertia. Let tau be the shear stress induced in the shaft. G be the modulus of rigidity. Modulus of rigidity. Theta, here you can see this theta is the angle of twist. Angle of twist. And L is the length of the shaft. You can see here if the shaft one end of the shaft is fixed and another end is free and torque is applied, so this torque is applied on the surface and this will produce a tangential force and this force will induce shear stress in it. So due to the shear strain, shear stress will be induced and we can find out the shear strain the shear strain is phi and it is equals to m dash upon L. You can see here tan phi equals to perpendicular upon base. Perpendicular is m dash and base is length. So tan phi equals to m dash upon N. Since phi is very small, so we can say that phi equals to m dash upon L. And we also know that this shear strain equals to shear stress upon modulus of rigidity. So m dash upon L equals to tau upon G. And from here, from the front circle, you can see that this is the center, this is the angle theta, this is M and this is M dash, and this is the radius R. So mm dash is the length of the sector and it is equals to R theta upon L equals to tau upon G. So we rearrange it. Tau upon R equals to G theta upon L. Till here we have performed half of our derivation. Now we move on to the elementary ring that we can see from the cross section here. This is the cross sectional view of the shaft. This is this is D, the diameter of the shaft. If we take an elemental strip of thickness dx at a distance of x from the center, so the turning force that is acting on this elemental ring, turning force on elementary ring, that is delta F, let us say dF for example, it will be equals to shear stress into area. Since the total shear stress acting on the shaft is tau, let us assume that a shear stress of tau x is acting on this elementary ring. Tau x is shear stress acting on elementary ring. So dF will be equals to tau x into area. Since it is circular, so surface area we will take 2 pi x. This is the circumference into its thickness dx. This is the area and this is the stress. Force equals to stress into area. This is the turning force that is acting on this elementary ring. Now if we want to find out the turning moment on this elementary ring, turning moment on elementary ring dt, it will be equals to df into the perpendicular distance, that is x. If we want to find if df is the force that is acting on this ring, then the turning moment will be df into perpendicular distance x. That means dt, now we will place the value of df here, that is tau x into 2 pi x dx into x. It will be equals to tau x into 2 pi x square dx dt. This is for this elementary ring. This dt is only for this elementary ring. If we want to find the turning moment, then we have to integrate this dt from where? From radius 0 to r. So we will integrate it from 0 to r. 0 to r tau x into 2 pi x square dx. Now tau x is also dependent term on dx. So we will now normalize it. Since earlier we can see that this tau upon r is constant. The ratio of tau upon r is constant. So we can say that at x the value of tau is tau x. So this ratio will also be constant. So tau x upon x will be equals to tau upon r. So tau x will be equals to tau into x upon r. We will now place this value of tau x in the downward equation. So here the total twisting moment T will be equals to 0 to r tau into x upon r into 2 pi x square dx. Here tau is constant, total shear is constant, radius of the shaft is constant. So we'll take this out, and now 2 and pi are also constant into 2 pi, and we will integrate from 0 to r x cube dx. From here we can find the value of t, and it is tau upon r into pi r to the power 4 upon 4. On integration we will get this value upon, sorry, here it will be 2 also. So it will be tau upon r into 2 pi r to the power 4 upon 4, and this will be tau into pi r cube upon 2. On solving, 1 r will get cancelled, and here 2, and we will get tau into pi r cube upon 2. We can also write in terms of diameter, the value of t in terms of diameter. So t will be equals to tau into pi by 16 d cube. We can find the value of twisting moment by this. We can also write here t equals to tau upon r into pi r to the power 4 upon 2, and this pi r to the power 4 upon 2 is the polar moment of inertia ip. Therefore t equals to tau upon r into ip, or on rearrangement it will be t upon ip equals to tau upon r, and from first equation we have also got equals to g theta upon l. This is the final torsion equation that is used to solve the numericals on torsion experienced by a shaft. That's all for the lecture. Thank you.